Okay guys, in this video we are going to get into this idea of polarity affecting the entire molecule and not just the individual bonds, okay, for this segment. So we left you with the question of if a molecule has polar bonds, is it always polar? And if a molecule has nonpolar bonds, is it always nonpolar? Okay, so we know that if you have polar bonds, there's always that potential of having a polar molecule. But because of this idea of symmetry, where sometimes polar bonds can actually cancel each other out, the answer to the first one is absolutely no. There are cases where we have polar bonds that still create an overall nonpolar molecule. The second one is a little less obvious. There are scenarios where you have nonpolar bonds inside a molecule that you will get a polar molecule. It has nothing to do with the bonds though. It actually has everything to do with unshared electrons sitting on a center atom. When you have a center atom that has unshared electrons on it, what you get is you get a molecule that does not have symmetry. So without the symmetrical nature of it, you have extra electrons sitting on one side of a molecule. Well, with extra electrons sitting on that one side, that generates a negative charge, which then creates a more negative area. So even though the bonds may be nonpolar, with things that are bent or pyramidal shape, you still get a polar molecule from them. So basically for here, nope, the answer is it does not happen. Now, if we take a look at our images down here, let's kind of walk our way through how do we generate polar molecules versus nonpolar molecules. So a couple of things we need to review is some symbolism. If you see these blue arrows here, what that tells us is that the less electronegative substance is here and the polarity moves to the right towards the more electronegative substance. Okay. Now you notice that every bond on here that we have a blue arrow except the carbon to hydrogen bond. If you look closely, there's a reason for that. The difference in polarity here, 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 and here are all above 0.4 but below 2, so they're considered polar bonds. The carbon to hydrogen bond is a non-polar bond. So with a non-polar bond, you wouldn't represent polarity. So this arrow wouldn't be appropriate here because it does not really have a polar bond to match with that. So we don't put the symbolism on these bonds. It doesn't mean that this doesn't affect our overall molecule, it's just these are considered nonpolar and really won't have much of an effect here. The other thing that we got to remember is this lowercase delta with a plus or minus symbol can also symbolize different sides of either a bond or a molecule being positive or negative. Okay, so let's start with water. Okay, water is our classic example. It's our easiest one to do as we look at it. So if we notice, we have hydrogen having less electronegativity than oxygen, and we have our polarity for bonds pushing both in this direction. So if you notice, it looks like all the electronegative or all the negativity sits on this oxygen. Everything is pushing away from the hydrogens, and oxygen also has extra electrons sitting on it. So if you think about this in terms of this molecule, all the negative charge is sitting on the oxygen, and very little of it sits on the hydrogen. As a result, even though we have polar bonds here, and we have a lot of negative charge on the oxygen, the molecule does end up being polar, not ionic, but polar, okay? And for water, it ends up being very polar. It's one of our most polar molecules we have. So the way we can actually represent that is we can say that this region of this molecule is going to be partially negative. This region of the molecule will be partially positive, or this will be a polar molecule. If we apply that same concept over here to our carbon dioxide, we see now that the oxygen is pulling away and this oxygen is pulling away. So it's very much like a tug of war, where if you have two equally divided teams pulling at the equal strength, there's going to be no net change here. Okay, this molecule has symmetry to it. Okay, it's a linear molecule that's symmetrical. So as a result, even though we have polar bonds, this molecule will end up being nonpolar. Okay, so with the symmetry, we have equal and opposite pull of our bonds. Now, if we go over to our last molecule in this example, we have formaldehyde here. We don't have polar bonds here, but we definitely have a polar bond here where oxygen is going to pull the electrons more to the top. Once again, there is not symmetry here, and we have an unequal sharing of electrons. So as a result, we get a negative side here where the oxygen is, and this other side over here ends up being more positive. So we get a polar molecule. What this means is, if this molecule now floats around in solution or in space, it's going to have kind of a negative side to it and a positive side to it, which of course will affect how it interacts with other molecules that may or may not have negative sides and positive sides to them. Okay, so kind of reviewing, we end up with a polar molecule here, a nonpolar molecule here, and a polar molecule here. Now, besides looking at symmetry and this idea of equal and opposite, there are actually some rules that we can use to help us out. Okay, so if we take a look, here's some rules when it comes to determining is a molecule polar or not. For any molecule to be nonpolar, okay, so for it to be balanced or evenly distributed electronic charge, it must have symmetry. Okay, so if you don't have symmetry, the molecule has to be polar automatically. No questions asked, has to be that way. Okay, so think equal and opposite with that. Now, we're going to break it down by molecule geometry or by type. If you're trigonal pyramidal or bent, they are always polar. So if you see trigonal pyramidal or bent, water, ammonia, these two up here, polar, no matter what. There's nothing else to think about. There's nothing else to worry about. It has to come down to the fact that there's unshared electrons on that center atom, so they generate polarity on their own. They're not symmetrical. Unshared pairs cause that. Okay. This is even true if our bonds are nonpolar, which is something that sometimes people get messed up. The bonds here can be nonpolar, but you will still get a polar molecule if it's bent or pyramidal. Now, when you go down to tetrahedrals, trigonal, planar, or linear, okay, all those molecules have the ability to have symmetry. Okay, so they could be symmetrical. But for them to be symmetrical, they need to have all the same exterior atoms. Okay? Because of that, it'll have symmetry. So let's take a look here. We have carbon. We have all the same exterior atoms. We have carbon with all the same exterior atoms. Again, carbon with all the same exterior atoms. In all three cases, these have symmetry to them. So these molecules all will be nonpolar because they have the same exterior atoms. Okay? Okay, so if I give you an example now where there is not symmetry for a molecule, what we'll use is we're just basically going to take carbon and we're going to bind carbon to nitrogen and then to a hydrogen. Okay? So in this case, we'd have carbon in the center. So we do have a linear molecule here, which means it could be nonpolar because it could have symmetry. However, carbon is bonded to nitrogen and hydrogen. Now, the carbon to hydrogen bond, this is a nonpolar bond. So if you do the math on that, this would not create polarity. However, the carbon to nitrogen bond has a difference in polarity of about 0.5. So it is a polar bond, which means you get a pull in this direction. Well, there's nothing over here to cancel that out. So even though we have a linear molecule, because of this polar bond right here, the overall molecule will become polar. We'll get this side being more partially negative and this side of the molecule being more partially positive. Okay? So you see an example where you have a linear molecule or something that could be planar or tetrahedral, that it would not be symmetrical. So the idea here is you're looking for those same exterior atoms to make things equal and opposite in their pulling. Okay, so take-home message: if you are bent or pyramidal, you are always polar. If you are tetrahedral, planar, or linear, you are nonpolar as long as all exterior atoms are the same. Okay, so that will really help you in terms of these decisions. You have to be able to distinguish this because the next step in our method is to start talking about the forces between molecules. And the different forces that we get between molecules are all dependent on if the molecule is polar or not. Okay? So we're going to end this segment here. Thank you for your time.